All right, welcome to video 18. In this explainer, we're really moving beyond the simple reflexes. We're going to dive into how those fundamental vestibular signals are, the actual building blocks for the brain's internal map of space. We'll see how this amazing system supports complex navigation, especially when you can't rely on your eyes, like when landmarks just aren't there.
So let's start with a clinical puzzle that's probably pretty familiar to you. Imagine this. A patient comes in and they're telling you they feel lost, right? They have this real sense of spatial disorientation, especially when they're in a new place. But you run the standard tests, your V-hit, your calorics, and everything comes back totally normal. This really sets up our core question. What in the world are we missing? What critical vestibular function are these tests just not designed to see?
Well, to get to the bottom of that, we've got to look at how the brain uses vestibular signals for something called path integration. And it's this really incredible ability to, internally track your position in space. It does this by adding up all your self-motion signals over time, even when you have zero visual feedback to go on.
Okay, so here's the breakdown. It all starts with that self-motion signal coming from the vestibular system, right? The brain takes that velocity information and basically integrates it. It does the math to figure out an updated position. But here's the crucial part. If that vestibular input is gone, or even just a little unreliable, that internal estimate starts to drift. It just accumulates error over time. And the result? Your patient feels totally lost because their internal map is now out of sync with the real world.
All right. So the first piece of this internal navigation puzzle is what you can think of as the brain's internal compass. And it's built from this fascinating group of neurons called head direction cells.
Now, head direction cells, or HD cells, they're pretty much exactly what they sound like. These are highly specialized neurons that fire like crazy, but only when your head is pointing in one very specific direction in the world. So, when you put all their activity together, the entire population of these cells gives you a continuous 360-degree neural picture of exactly which way you're facing.
Okay, so how does the brain keep this compass updated in real time? Well, it relies on a direct line right from the vestibular system. Those angular velocity signals, they travel up from the vestibular nuclei through some key spots in the brainstem, like the dorsal tegmental and lateral mammillary nuclei, then they relay through the anterior thalamus, and finally, they update that directional map up in the cortex.
A really great way to picture this system is as something called a ring attractor. Just imagine a ring of neurons, and on that ring, there's a bump of peak activity. That bump represents your current heading. Now, as you turn your head, it's the vestibular angular velocity input that literally pushes that bump of activity around the ring. It's just a really elegant, continuous way to keep your internal compass pointing in the right direction.
And this brings us right to a crucial clinical link. What happens when that vestibular drive fails? Well, the internal compass becomes unstable. It just can't update correctly on its own and needs visual cues to keep resetting it. And that right there, that explains exactly why a patient might tell you they feel completely disoriented in the dark. Their internal sense of direction has lost its main update signal, the one that doesn't rely on vision.
Okay, but look, a compass is only half the battle, right? You also need a map. And that brings us to the second system, what we can call the brain's cognitive GPS. This whole thing is built on the absolutely incredible firing patterns of grid cells.
Grid cells, they're found in the medial entorhinal cortex, and they are just truly remarkable. See, unlike a place cell that fires in just one spot, a grid cell fires in multiple locations as you move through an environment. And as you explore, the spots where it fires form this stunningly regular hexagonal grid that basically tiles the entire space. What this does is give the brain a built-in coordinate system, a way to measure distance and direction.
Now, for this grid map to actually be useful, it has to be stable. And that stability, it hinges on two different inputs. It needs vestibular input to do that path integration we talked about, to update your position on the map as you move. But, and this is key, it also needs visual landmarks to anchor the map to the real world and to correct for any drift that builds up over time.
This dual dependency, that is the absolute key. Without that vestibular input, the internal GPS just drifts, and without visual anchors, it can't fix itself, so it gets misaligned with the world. This directly explains those patient reports we hear all the time. I feel so lost in the dark. That's path integration failing. I can't navigate without constantly looking around. That's them trying to compensate by using only visual anchors.
And there it is. This is the answer to our opening question. Spatial disorientation, difficulty navigating, these are vestibular symptoms. They're a sign that this higher order vestibular processing has failed. Our standard tests? They're brilliant at probing the VOR, that short latency reflex, but they simply were not built to pick up on deficits in these complex cognitive mapping circuits.
So let's boil this all down. What are the key clinical takeaways here? Let's connect the dots between this neuroscience and what you're seeing every day.
Okay, 3 things to remember. First, vestibular angular velocity is the engine that drives the brain's internal compass, the HD cell system. Second, the brain's GPS, that grid cell map, it's a partnership. It needs both vestibular input for path integration and visual landmarks for anchoring. And finally, and this is probably the most important point, when a patient comes to you complaining of feeling lost, that is a legitimate vestibular symptom, one that our standard reflex-based tests are almost certainly going to miss.
And this really leaves us with a provocative thought to chew on. When we see a patient with that so-called unexplained dizziness, the ones with normal VOR tests, we really have to start asking ourselves, how often are we actually looking at a primary failure of the brain's cognitive map? So we've covered how vestibular signals support the cognitive map. Next time in video 19, we'll dive into recovery and rehabilitation. We're going to translate all this neuroscience into a real mechanistic framework for rehab, showing why things like VOR exercises, sensory reweighting, and graded exposure actually work, right down at the level of synaptic plasticity and prediction error signaling.
Thank you for listening. If you want to explore more on dizziness, vertigo, and imbalance, or access resources for clinicians and patients, just head over to AustralianDizzinessClinics.com. And of course, please don't forget to subscribe and leave a rating.